Good morning, everyone. Happy Monday. Happy almost end of the trimester. We basically have 4 days this week and 2 days next week, and we're done with try two. All right, let's go over this problem here. This is actually taken from an old AP exam, and it's a very common style of problem. They say that if we know that the area under the curve of f of x dx from a to b is equal to a plus 2b. So we're going to use this, and then we have to evaluate the integral from a to b of f of x plus 5 dx. Well, this part right here tells me I need to split up the property. I have to use the properties of integrals to split this integral up because I don't have f of x plus 5. I just have f of x. So what we're going to do is, you might not have shown all of this work, but if I'm given the original integral, we know that we can split this up as two separate integrals, just like that. Now, what's the benefit to doing that? Well, we know exactly what the integral from a to b of f of x dx is. That's equal to a plus 2b. So we don't have to do any calculus for that. It's just we know the answer. The next one, we have to actually evaluate. So I'm thinking, whose derivative gives me 5? Right? Well, that's 5x. And then I'm going to evaluate that from the upper bound minus the lower bound. And we're going to just add those together. So if I plug b in first, I get 5 times b minus 5 times a. And then we get a plus 2b dropping down. And my sum is just combining like terms now. So I've got my a minus 5a. So that's going to be negative 4a. And then I've got 2b plus 5b, so that's 7b. And then answer C is the answer that we need. So perfect kind of just quick review of a property. The reason why I put this one up here was to see if anybody wanted to try to do use substitution. And the reason why we can't is because we would then have to take the derivative of f of x, which we don't have. So this is just a property of integrals. Okay. Before we get started, I want to make sure that everyone is clear on this. So did you pay for the AP exam yet? The final deadline for making the AP payment is now February 28th. And at that time, after the 28th, the window would be closed and any unpaid exams will be removed from Tartan's order, which means you will not be able to take the test if you do not pay for the AP exam. You don't have to write this down. I want to kind of just give you an overall view of what have we done really this whole unit 6. So the last test and then this little mini test that's coming up here. It's called Techniques for Integration. Well, what did we do? We found methods for solving integrals. And the first part was just use the chart that was given, right? If we know the chart, we can evaluate it. And that was just using the antiderivative. And then we talked about algebra. We actually were hinting at algebra well before we even did anything with substitution, so maybe these should be flipped. But can I factor something out, or can I rewrite a problem so it looks easier? Then we did use substitution, and that was what we learned last week. We're going to do more use substitution today. My guess is you're probably fairly confident in it, but we just need a lot more practice with it. And then we have 2 new pieces today that are just little kind of subcategories of these, that what happens if I can't just take the antiderivative, or I can't do use substitution, or algebra doesn't work. Maybe it's a long division, and maybe it's completing the square. So we're going to introduce 2 new pieces today. I'll give you a little hint. Both of these are potentially topics that could be on the AP test. I've seen both of them. However, I've seen them in one multiple choice question. And I'll let you know we are going to have a long division problem on this test, the mini test coming up at the end of this unit. We are not going to test on completing the square. However, we are going to show it and practice it in the homework. Okay, we don't have time for this. In years past, I've done this as a longer warm-up. However, there's a pattern that I just want you guys to see. So what I did was I actually worked through these, and you can kind of see they're almost all similar, right? I've got 3 plus 4 over x plus 2. Well, I've got a fraction, and I have a fraction here and a fraction here, and in those fractions, all it is a polynomial in the bottom. So watch what happens and see what we got here. So I'm going to show you the first one. First option is this 3, we're going to split up, just like we did in the warm-up with that 5. And then I'm going to take the 4 that's up here and just rewrite that to the outside. So we know the integral of 3 is 3x. That's the blue part. But what about the integral of 1 over x plus 2? Well, this integral is a u substitution. We're going to let x plus 2 be u. And notice, and this is the important part of the pattern, notice when I take the derivative of that, all that's left is a dx, which takes care of this dx. So du replaces dx. X plus 2 is replaced by u, and now I have 1 over u. So the antiderivative of 1 over u is the natural log of u with the absolute values around it. And then we just plug u back in, and don't forget to add the plus 3. Okay, so that's what I would consider a pretty friendly u substitution problem right now. Well, look at this. It's very similar, except for now I have 2x and a different constant up on top and a different linear polynomial on bottom. So if I go in pieces, what would you do first? Well, we'd split this up. 2x would be in its own integral, and 5 over x minus 3, but the 5 would come out as a multiplier. And a lot of times students forget about that 4, the 5, even the negative 7. That's a multiplier. And our goal is to just make these integrals easier to look at. So then what we would do, we'd let u be the bottom part of the fraction. And when I take the derivative of that, notice just the dx is gone. So we made this a much friendlier integral as 5 of the integral of 1 over u du. So u substitution is what makes this possible. And then over here, the antiderivative of 2x, well, that's just x squared, right? And notice the integral here is the same integral here. It's 1 over u, so it's ln of absolute value of u, and then just replace u. Okay, and then add plus c. So you might be seeing a pattern right now. When you see a fraction and it has a linear portion in the bottom, you know it's going to be a natural log. Okay, so same thing here. So what would I do on this one? Well, I would first move that negative 7 out because I want it to be 1 over something. And then that bottom part is what our u is going to be. Now this one's just a little bit more. Notice how it's got a 2 in front instead of just an x. So when I take the derivative of that, I get a 2 dx. Well, I have the dx, but this extra 2 is not represented, so I have to move it over with the du. So it's a 1/2. And then I'm just going to replace the negative 7 stays. Dx is going to be replaced by 1/2 du, but instead of putting 1/2 in here, that's another multiplier, so I'm going to put the 1/2 outside. And notice, it's the same integral now as the other ones. So 1 over u is the natural log of the absolute value of u. And then negative 7 times 1/2 is negative 7/2. And then we just replace u. So this is just a common theme. And I'll show you today why we had to review this, because this comes up within long division. Okay. What I want to do first is give you guys a little bit of feedback. So we're going to go, let's try 10 minutes on this, and if we need 2 more, we'll do that. But at 11:20, we're going to go over these 3 answers, and your job is to evaluate the 2 integrals here, and then this integral has the limits, so just be careful with those limits. By the way, this will be a really good review for the test that's coming up this week. May or may not have had a chance to do all of these. I have these preset just so we can go over them a little faster. And let's look at number one here first. So one of the hard parts with problems like this is deciding what value to let our u be. And here's a hint. We have an inside function here. And that's usually your best bet. And the reason why is if I can rewrite this as u squared, that makes things a whole lot better. But the only other question is, why is this the correct u? Well, if I take the derivative of that, notice its derivative is a positive sine t dt, and that value right here is shown right there. So I can replace this sine and this dt with du. Now notice the 3, I'm going to float that to the outside because that's a multiplier. I want to make this look as friendly as possible. So that's where u substitution gets me. And then I have u squared. So it's in the denominator. I don't love that it's down there. I'm going to just rewrite this as u to the negative 2 because now I can undo the power rule by adding 1 up top. So if I add 1 to negative 2, I get a negative 1. But if I put a negative 1 up top, I kind of have to divide by negative 1 or times by the reciprocal. That's what I did here. So that turns into a negative 3, and then we just replace the u with 2 cosine of t to the negative first power. This first answer could be accepted. However, it's probably a multiple choice question, this would be, so it would be written most likely this way right here. And you might be thinking, well, what happened to the power of 1? The negative brought it down in the denominator, and then all I have to do is I don't have to put a power of 1 there. And then just don't forget your c at the end, right? The plus c. Okay, let's look at problem number 2. Now this one right away, hopefully you're seeing bounds. The other thing I hope you see is, okay, I've got a more complicated problem, so I have to do u substitution. And what we usually look for is there an inner function? Since u substitution is undoing the chain rule, we're looking for that inner value, which is x squared minus 2. Now, right away, before I even write anything, think of the derivative of this, right? The derivative is going to have another x in it and a dx. So I know for sure before I even start this problem that this x and this dx are going to go away and become du. Now there is a little bit more, so we got to be careful. See if I can show at least the part that I did. Okay, so I let u equal x squared minus 2, and then I took the derivative of that, and that's where the 2x dx came from. Now notice, I have the x and dx, those are right here, but I do not have an extra 2 to account for this. So that 2 has to move over, and I get 1/2 du equals x dx. Well, the 1/2 du is going to replace this green x dx, but instead of putting the 1/2 in the integral, that's a constant, so I float that out. All right, the u is replacing the yellow x squared minus 2. And then the only thing we have to worry about are the bounds. And that's the part we got to be careful with is we want to change the bounds. So right now, the original bounds are written in terms of x. We're going to rewrite them in terms of u. So I'm just taking whatever I called u and plugging in the upper bound. So I get negative 1. And then I'm plugging whatever I call u, I'm plugging 0, the lower bound in it, and I get a new upper and lower bound. All right, so now u substitution made this integral easier. So whose derivative gives me e to the u? It's just e to the u, and the 1/2 is going to drop down. And then we just have to evaluate it from the upper and lower bounds. But notice those are now written in terms of u. And since these new bounds are written in terms of u, we do not have to replace u with what it was equal to before, because this just makes it easier. So now if I plug in negative 1 and negative 2, you could write your answer like this, or if you distributed the 1/2, it could look like this. Okay? Or it could be just the 1/2 in front of each one of these and have it as a negative exponent. There's multiple ways to write this. All right, and then let's look at the last one. I think this one's kind of tricky. And the reason why is because the fractions. A lot of times students aren't super familiar with the fractions. So what's my first option? Well, I've got a integral here that is a little more complicated. But I do notice that it has an inside portion, right? X to the 1/3 minus 4. If I let x to the 1/3 minus 4 equal u, the 4 is going to go away, and then the derivative of x to the 1/3, well, the 1/3 comes down, and I'm left with a negative 2/3 dx. And that negative just means that portion will be in the denominator. So I have the negative 2/3 and I have the dx right here. The only thing that I didn't really take care of is that 6, which is absolutely fine. We'll deal with that 6 in a little bit. But this 1/3 is not present here. Now, some students like to split up the 1/6, and some textbooks do that. I would just say, let's just move this 1/3 over to the other side and call it 3. So 3 du is going to replace this green x to the 2/3 dx. So let's go to substitution. Here's a hint. See this 6, the divide by 6? That's a constant, right? I can put a 1 up top, and I'm going to float out a 1/6. 1/6 is the same as dividing by 6. So I took care of this 6, and then the yellow part was replaced by u. The green part is replaced by the 3 and the du. And I really don't need this divide by 1. But now it's just a power rule. I'm going to add 1. We're going to undo the power rule, so we'll add 1 to the 5 and put a 6. But if I put a 6 up here, we got to put a 1/6 out in front. It's a multiplier. And then the 1/3 and the 1/6, when you multiply those, they become 1/2. And then the last part is 1/2 times 1/6 is 1/12. And replace u with what it was equal to. And then just don't forget your plus c. All right, so quick refresher. Anything that doesn't have bounds, that's called an indefinite integral. You need the plus c. We don't put the plus c when we have bounds because the constants automatically will take care of that constant value. Okay, I will be posting these notes, so if you didn't catch everything there, you can always go back and look at them quick. And I want to show you these two examples. It's up to you if you want to write them or not. They're actually pretty quick, but they're trickier ones that sometimes students don't always see. All right, so I'm going to go through these hopefully quickly. First thing I'm going to look at is, okay, and don't write this part because you're going to actually see it's not going to work. But the first thing I might say is, excuse me, I don't love this. I don't recognize it. So what if I thought about taking, oh, sorry, there's a question. So wait, the negative 2/3 can replace the positive. Oh, so let me go back to this question to answer. Notice this 2/3 here is in the denominator. It's in the denominator. If I was to rewrite it, I could write this 2/3 up here and call it a negative 2/3, and that's why it would replace here. So I just didn't rewrite this, but anytime it's in the denominator, you could rewrite this with a negative exponent, and that's how it was replaced. I think that, hopefully that answers the question. All right. So let me show you this. Don't write this part, but I see this often, and I think this is a really good problem to do that. So x squared plus 1. A lot of times students are like, well, if I could get rid of that, it would make this an easier problem. Watch what happens though. When I take the derivative, I get 2x dx. And I don't have an extra x. So this x right here is causing us a problem, which means I cannot use u substitution here for this problem. So that is one case where it just doesn't work. But if we're able to do this, what else could we do? Well, here's my advice. I don't love the 3, right? That 3 is a multiplier, so let's pull it out. And then we're thinking, wait a minute, whose derivative gives me 1 over x squared? And if you remember that, that is kind of, do you have full mastery of your derivatives to figure out in reverse, whose derivative gives me 1 over x squared? And all that is tangent of x. So then the 3 would come down and the plus c. We haven't done a ton of those, and they're not super, super common, but they do appear. Here's the rule, by the way. This is from that chart on page 439 that I showed you the other day. If you see 1 over 1 plus x squared, now notice these are flipped, but it's addition. So I could rewrite this as 1 plus x squared and it would match. So I would just say, this is my rule. Whenever I see this, which by the way, we are going to see this today, that's why I'm showing it to you now. The antiderivative of 1 plus x squared is tangent inverse. And you can kind of guess the same thing here. Now this one is a little bit trickier. So really pay attention to this one. And you know what? I don't want to waste too much time today. We are going to do no bounds on this one. I just want to show you so we'll get rid of the bounds. Okay. Now again, somebody might think, well, wait a minute, this is under the square root. If I let u equal 4 minus x squared and I try to take the derivative of that, I get a negative 2x dx, but I don't have an extra x in here. So that's why u substitution doesn't work. And it's good for you guys to understand that u substitution does not always work. So what would I have to do on this one? And on this one, I'm going to actually show you the rule right away. Okay. Here's my rule for the inverse of sine. I need the square root of 1 minus x squared. Well, I almost have it. I just have this 4. I have to turn that 4 into a 1. So how do I do that when something is in a square root? Well, remember fractions, you can multiply by a common factor, and this is going to look a little weird, but I'm going to multiply by the top and the bottom by 1 over the square root of 4. Okay. Why did I pick that? Well, when I put a square root in here, if I can get this to be the square root of 4 over the square root of 4, I can make it turn into 1. So that's my reason why. And again, you'll see how this works. Well, there's properties we could do. This would be multiplied by the top part, but I'm going to leave that out because I don't want this to be anything other than 1. However, I'm going to take the bottom, I'm going to multiply it in. All right, so the top part right here is going to stay on the outside. And then on the bottom, I'm going to have I'm going to erase this part, but I just want you to see it. So I'm going to multiply by the square root 1 over the square root of 4 into this. And when I do that, instead of writing it on the outside here, because this part is a radical, and by the way, I could put that as the square root of 1 as well. That's really like taking both of these pieces and dividing. So instead of timesing here, I'm really just dividing by the square root of 4, which is really what we're doing here. Okay. So what the bottom turns into, actually, square root of 4. I don't want the square root of 4. I want this to turn into 1. I want, no, that's right. Sorry. When I do this, this will turn into the square root of 4 over the square root of 4, which is 1. And then the tricky part here is I've got x over, and I should put this square root over, the x squared over the square root of 4 well, what if I rewrite this where I square the bottom 2? So then that just becomes 4, right? Because I can rewrite the bottom as squared, and 4 squared is the same value here. Actually, I take that back. This would have to be a 2, right? Because if I put the square root of 4 is 2. Anyways, what this ends up doing then is this gets us almost in this form. The only difference is instead of an x divided by 2, we have just an x. And now we could do u substitution here. And let the u value be whatever this inside is, because I changed everything into this form except for x is not exactly the x. And you might not be perfectly comfortable with this right now, which is fine. I just wanted to get you to start thinking about this. So this 1/2 is not part of my original problem, so I got to bring it out here and multiply by the reciprocal. And then I can have the 1 over, now notice this is really going to be 1/2 here, right? Square root of 4 is 2. And then we call the x over 2 is u. And then the du, the 2 du is going to replace the dx that I actually forgot to drop down. There's my dx. And then the 2u is going to come out in front. So the 2 and the 1, that's going to just reduce out. And this whole piece is going to be the inverse of sine of u plus c. And then if I realize I'm going to write u here, but I know what u is equal to, I can rewrite it. So I know you probably don't love that example right now. Completely fine. Okay, I wanted to show you the tangent one's a little friendlier because there's no square root. The sine one, just a little bit trickier. Okay, but our goal is to get this number to be a 1, so then I could apply the rule. All right, so what we're going to do today is just a quick reference. This was, I wanted to show you this because I didn't just pull those 2 rules out of thin air. Right? Here was the one rule that we just talked about. That's the sine inverse one. And then the other one was this tangent. Okay, so hopefully you either took a screenshot of this from the day before or you have page 439 bookmarked in your textbook. Okay, this is what I want you to write down. We're going to do something a little bit unique, and I think you'll like this one. Long division isn't too bad. Completing the square is a little more challenging, but how do we know when to use long division? Okay, how do I know to use this method with evaluating integrals? Well, there's 2 ways to think of it. Well, first off, u substitution is not going to work here, right? If I let the bottom be the u, well, the derivative of that is going to have an extra x in there, and it's not going to get rid of anything up here. So hopefully you can kind of see without writing it down, u substitution does not work. So when integrating a fraction where the degree of the numerator is greater than the degree of the denominator, then you have the option to use long division, okay, or split the fraction up. Now notice, greater than or equal to. So that's our hint. Is the degree in the numerator greater or equal to the degree in the denominator? And since 2 and 2 are equal, then long division actually is something we could do. So I'll give you a second to write down anything you need to here. Okay, so once we determine that the degree in the top is larger or equal to the degree in the bottom, we're going to set up long division. And it's probably been a while since you've done this. I know we do it in pre-calc, but I'm going to take the bottom, x squared plus 2. I am going to put a place value in there because we are missing that 0x. And then we're going to do long division by dividing, seeing how many times does the denominator go into the numerator. All right, now if you remember how long division works, we want to find something to multiply this trinomial so it matches perfectly with this one. Well, x squared matches with x squared, so I'm just going to multiply by 1. I usually draw these arrows in. So 1 times x squared is x squared. 1 times 0 is 0x. And 1 times 2 is 2. And then if you remember how long division works, we always add the opposite. So I like to match it perfectly and then say add the opposite. So I change the sign values to make that a different color so it appears better. So we add the opposite sign. And then in that case, we get an x squared plus a negative x squared. Those go away. Negative 4x plus negative 0 is just negative 4x. And 2 plus negative 2 is 0. I'm not going to write that. Okay. So there's the long division. And we do that now so we can rewrite the integral. I want to rewrite the value of this and talk about, well, okay, well, what is it? It's 1 plus the remainder over whatever we divided by. Okay, so I tried to color coordinate this. You can see where the 1 comes from. And then the remainder divided by whatever the original denominator was. Well, now you can split this up into 2 different pieces. Okay? And I do recommend doing this just proper notation wise. Right? This 1 we're going to evaluate separately. And then we're going to evaluate this integral separately. And I personally, what I would do, this minus 4, I would pull that to the outside because that's not really going to help us. And now it's just like doing 2 separate problems. This integral is very quick. Whose derivative gives me 1? It's x. Now, I'm not going to put this plus c right here. The reason why is that's a constant, and I'll have a constant for this one, so I'm just going to write the plus c at the end. That's why we don't write it twice. Now, this is just like what we did before. Now I have a u substitution that can actually work because I have an x squared and my degree on top is less than the degree on bottom. So that's why long division basically reduces out at least one factor, maybe more, and allows us to go ahead and do u substitution. So I know what u is. I'm going to take the derivative of u. I'm going to move this 2 over to the other side. The reason why I move the 2 is I don't have a 2 present. Now, some people might argue you can take the 2 away from this, but it gets confusing when you do that. So I'm just going to make sure that I have a 1/2 put in here as we go ahead and simplify. All right, so the negative 4 is going to drop down. I'm going to rewrite the integral of 1 over u. And then this dx, or excuse me, x dx right here is going to be replaced with 1/2 du. But instead of putting the 1/2 up here, I'm going to float the 1/2 out. You could write du right here. I don't love doing that. I like to put it on at the end. And then that does mean there has to be something there in the numerator. But then there's that very friendly antiderivative again. 1 over u is the natural log of u. Now, to save time, I know that I'm going to write u here. But we know what u is. So we might as well just replace it right away. And then I just got to make sure everything else is included. Right? The x drops down. And then I've got -4 and -4 and 1/2 being multiplied together, so that'll just be a -2. And there's my final answer. Okay, so long division is another tool that we have to use if we can't find out the integral in any other way. Let's try another one just to give you guys a little more confidence in it. Now you'll notice on this one specifically, notice the numerator is larger than the denominator. So right away, that's an indication that long division is possible. All right. I want to show you one thing also. Don't write this, but a lot of times students might try to do this. So they might say, well, I've got a 3x. What if I let 3x be u, and then I take the derivative and I move the 3 over. Okay, now be very careful here. Just because I see an x squared does not replace this x squared. This x squared is in the denominator. This is a positive value. So this x squared is not the same as this one, which means this u substitution does not work. It is not correct. So what we have to do is long division. Okay? And we're going to take the denominator and see how many times does it go into the numerator. Keep in mind that this is an x squared plus 1. There's always that place value of a 0x that you have to be aware of. Just like there's the place value of everything after the x to the third. There's a 0x squared. We might not need all of these, but all of those place values are true. So now I want to take this trinomial and make it match perfectly with the x to the third. So what's going to take a squared and turn it into a third? Multiplying by an x to the first power. And we always multiply all of those terms together. The nice thing is this 0 is going to give me a 0x squared. And I do have a 1x here. Okay? And then we always add the opposite. So I just make these the opposite sign of whatever they are. And then we add them straight up and down. So the x to the thirds go away. So do the x squareds. But I do have a negative 1x plus 0. And then notice this is an x squared and this is an x to the first power. So I can't go any further, which means I really don't even need that plus 0. That doesn't do much for me. There's my remainder. And this allows me to rewrite the original integral. So my new answer is x plus the remainder over whatever we were dividing by. All right, well now it's basically the same thing we just did, except for we have two integrals. This one's just a little more challenging than the other one. The official property does say we should split this integral up into two separate ones. And I'm going to rewrite this. I don't love this -1 right here, so I'm going to pull that -1 out front and just leave it with an x over x squared plus 1. And then this one's very friendly. Whose derivative gives me x? It would have to be 1/2 x squared. And then for the next piece, now we have to do the u substitution. I want that bottom of the denominator, x squared plus 1. I want that to be my u. Okay? And then we can take the derivative. But you'll notice I don't have the 2 present in the original integral. So I'm going to move the 2 over. Then I have exactly what I need. I've got the x dx. Those match up. So I can replace this part with 1/2 du. And I just float that 1/2 to the outside. And then just don't forget, this was -1 times 1/2. And then notice, again, this is a natural log. Most of the times, if you can do long division, your antiderivative is going to be a natural log anyways. So I know this will be the natural log of u, but to save time, I know what u is equal to. And then out front, we get a -1/2 when I multiply those. And the second piece drops down. Okay, so you will have 3 problems that are like long division in the homework tonight. And I want to see if we can get to the completing the square. We got about 13 minutes left. So there are some homework problems on completing the square. They're not super easy, so we'll see how far we get here. It's not horrible, though. Maybe you might like it. Completing the square. What students struggle with this is thinking about how we say completing the square. So just think of an example like if I had x squared plus 10x plus 25, remember how that can be factored into x plus 5 times itself, which is a better way to write it as x plus 5 squared. Right? So this is a perfect square trinomial because 25 is our perfect square and 10 is 5 plus 5. So like let's say I wanted to do x squared minus 4x plus something. Right? Well, what would have to go here? Actually, it has to be yeah, that's right. The only thing that would go here to make this a perfect square would be a +4. And the reason why is an x minus 2 and an x minus 2 multiply together to give me +4, but add up to give me -4. And then I would write this as that perfect square. So that's the goal, is we want to turn the denominator into one of those perfect square trinomials. So I want the last part of that perfect square to be a perfect square number. Well, 8 is clearly not a perfect square number. But I can get creative with this. So my goal is to split up 8. I want to rewrite 8 so I can have x squared plus 4x plus something that gives me a perfect square. And we kind of knew, instead of this being plus, this one was a minus, but I want this to be a 4 right here. So I'm going to split up 8 as 4 plus 4. And I like to use a separate color here. So notice, I didn't do anything inappropriate math-wise, right? 4 plus 4 is still 8. I just rewrote that. But the reason why is now I want to think of x squared plus 4x plus 4, and then this extra 4 we're just going to leave off to the side right now. Well, I can factor that, right? So this now becomes this is x plus 2, so 2 times 2 gives me 4, and 2 plus 2 gives me 4. So instead of writing it out like this, I'm going to just say, well, isn't that the same as x plus 2 squared right here? And then I just have this extra 4 pushed off to the side. And we're still taking the integral of that. Now, this is getting really close to something that, don't write this part, but if I had this, right, 1 over x squared plus 1, that was the inverse of tangent plus c, right? So we're getting to this fact that we talked about earlier. My question is, how do I get rid of that 4? That's the tricky part. Now, what I'm going to do is I'm going to divide this by 4, but whatever I do to the bottom, I have to do to everything in the bottom, and I have to do to the top. So notice, if I divide by 4, what happens? I get a 1/4 up top. But in my rule, I want this to be a 1. So I'm going to actually float the top 1/4 out as a multiplier. And then in the bottom, I get 4 over 4, which is 1. And here's where we get a little creative. Okay? Another way to write 4 here is 2 squared. So then I can write the bottom part as x plus 2 over 2 squared. So notice this blue 4 is officially outside of the parentheses. But if I rewrite it as 2, then I can put that 2 inside. All right, so now we are at the point where I am almost in the perfect form. I have a 1 on top, I've got a plus 1, and then all I have is a very busy value right here. So we're going to let u equal x plus 2 over 2. Remember, that's the 1/2, right? So I could rewrite this as 1/2 x plus 1, right? If I just divide each one of these by 2. And that makes it easier to take the derivative. Because when I take the derivative of 1/2 x plus 1, I get 1/2 dx. But I don't have a 1/2 fully present. So I'm just going to move that 1/2 over. Okay, so what do we have now? We're going to replace x plus 2 over 2 with u. The du is going to replace the dx, but there's an extra 2 there. Well, now, this integral is in the perfect format for the inverse of tangent. So then my answer, maybe I'll do that in blue, is tangent inverse of u plus c. And then out front, I just have a 2 times 1/4 or 1/2. And the very last step is just to rewrite this with the u. And we usually write the original u value instead of the algebraic manipulated one, but it doesn't really matter. And it was all based off of this rule from down here. Okay, first thing, I don't love the 5. So I'm going to push the 5 to the outside, and that way I have a 1 over something. Now here, I want this to be a perfect square. So I want to think, well, wait a minute. Isn't this the same as negative 4x and negative 4x? And if those are multiplied together, couldn't I get 24 to be a 16 somehow? So if you remember completing the square, we cut this in half, and we get negative 4, and then negative 4 squared gave me positive 16. Now, I'm going to move this over really quick. Okay, so I've got x squared minus 8x, and then the 24 is going to be rewritten as 16 plus 8. So that's really the only thing I did was I pushed the 5 out, and I just split up 24. Now, why would I split up 24? Because I can factor this inside, right? By factoring that, that turns into x minus 4 times x minus 4, or x minus 4 squared. Okay, so the green part is why it's called completing the square. After that, the only spot that's tricky is this 8. And I don't love having this 8 there. I need it to be a 1. So I'm going to divide everything by 8, top and bottom. And that way it's equal values. I didn't change the meaning of this. I changed the appearance. But the 1/8 out front is going to, up top, is going to float out front. So then I just have a 1 up top. 8 over 8. Now this turns into 1. Right? And then here's the tricky spot. How do I rewrite this? Because I need an 8 over here. And there's more than one way to do it. But what's equivalent to dividing by an 8? You could divide by the square root of 8. Now notice, if I squared the top, it would stay. If I squared the bottom, that would turn into an 8. So that's the one tricky spot, is when you have the divide by 8, it has to be absorbed into the square for me to do my u substitution. Now I'll let u equal the bottom part, and then we are going to just rewrite this so it doesn't look as hard to take the derivative. Then when I take the derivative of this, I don't care about the negative 4th divided by the square root of 8. That's a constant. It's going to go away. And x divided by 8 is the same as 1 over square root of 8 times x. So its derivative is just 1 over square root of 8 times dx, and then just move the square root of 8 over. Okay? And now, unfortunately, I don't have enough room, so I'm going to have to go back the other way. I have 5 times 1/8, or 5/8, is 1 over u, so we're going to replace this whole thing with u, and then the du has an extra square root of 8 in it. The square root of 8 du, and this whole piece turns into the tangent inverse of u plus c, but we know what u is, x minus 4 over square root of 8. I don't think the homework is anything as ugly as this one, so if you follow this one, you're in a really good spot. Okay, I want to just make sure you're aware of what's expected this week. I know I'm a minute over, but tonight's homework is 6-5 day 2. I'll show you what that is. Tomorrow you're going to watch a video. Thursday we're going to review in class. And then the chapter test is a mini test. It's 5 questions, 22 points. Oh, I'm sorry, 7 questions. One of them is the academic integrity statement. The other one is 4 multiple choice questions and then 2 uploads. And we're going to do U substitution with and without limits, long division. There is no completing the square questions on this test. If you want to see this a little bit more in detail, we'll go over it on Thursday. But here's the homework for tonight. And if you didn't pay for the AP exam, please do so. All right, that's all I have. Have a great day. I'll be available in my office hours if you have any questions.